All right, I think I have to start the lecture. So we're gonna start the lecture, and this is Chemistry 409. As usual, your course facilitator is Professor Napokedi. The course deals with electrochemistry. We should look at what the outline looks like. The outline for today's lecture: polarization at interface. And before then, we shall look at we shall introduce what is polarization. We shall have from expected learning outcome, then expected learning outcome shall be outlined. Polarizable and non-polarizable interfaces. Last time we talked about three major types of interface: solid, solid-solid interface, solid-liquid interface, liquid-liquid interface. So we look at polarization and non-polarizable interface. Polarization of a single electrode, dependent on activation over potential on current, Tafel equation, Boltzmann equation, and then before we conclude this lecture. So our expected learning outcome, we expect some expected learning outcomes shall include that to have a good understanding of polarization. I stated earlier that polarization arises when you pass a voltage, you pass a current over an electrode. Some electrode will lead to a change in voltage, significant change in voltage, while some will not change. And that's where you have polarizable and non-polarizable interface. It's based on the response of electrode system to apply current. Then we should know the different types of polarization. We shall see there are different types of polarization. We shall see anodic polarization. We shall see cathodic polarization. We'll develop a solid plot for cathodic and anodic polarization. We shall derive Tafel equation, and you try to know how to deduce information from potential dynamic polarization plot, and then you should be able to derive the Boltzmann equation using the Tafel equation. The application of a small current or potential to electrochemical system will likely create a linear response. If you recall Ohm's law gives you a linear response between current and voltage. You see, IR is equal to voltage. So that means current is V over R. That means you plot a plot, or let's say a resistance. If you look at IR is equal to voltage, that means if you plot, if you try to divide, let me put it down. IR is equal to V. That means a plot of V against current should be linear, passing through the origin, and the slope should be resistant. So that relationship has been obtained for several electrochemical systems. The effective resistance can vary over a wide range of values, but when it is high, a polarizable interface is created. What is a polarizable interface and how is it created? In a polarizable interface, a small current generates a very high potential across it. That means, just like I've said, you have IR equal to V. When the current increases, the voltage will increase and it will be very high. That is a polarizable interface. When the effective resistance is low, a significant current can be passed through it and the observed change will be minimal. In polarizable electrode, there is no Faraday current between the electrode and the electrolyte. A Faraday current exists in case of non-polarizable electrodes. So this is the relationship as I've stated before. So you can try yourself in some of these questions, differentiate between polarizable and non-polarizable interface. How can you make a non-polarizable electrode to be polarized? That means you increase the current. When you increase the current beyond a certain threshold, it will become a polarized interface. So in a polarizable interface, a small current generates a high potential across it, but in non-polarizable interface, significant current generates little potential across it. That is the difference. In polarizable electrode, there is no Faraday current between the electrode and the electrolyte. But Faraday current exists in case of non-polarizable electrode. Those are the two major differences. A non-polarizable electrode is in effect a reversible electrode. A good reference electrode is always a reversible electrode, but not all reversible electrodes are suitable as reference electrodes. The potential of polarizable electrode is not fixed by the solution composition, and it can be changed at will over a certain range, depending on the metal and the composition of the solution in contact with it. For non-polarizable interface, the non-polarizable interface can be changed, can be polarized by passing a significant current through it, and the concentration of both the reactant and the product at the electrode surface will be altered without changing significantly their bulk concentration. Polarizable and non-polarizable electrode. A non-polarizable electrode is in effect a reversible electrode. A good reference electrode is always a reversible electrode, but not all reversible electrodes are always suitable as a reference electrode. Polarizable interface behave differently. Their potential is not fixed by the solution composition, and it can be changed at will over a certain range depending on the metal and the composition of the solution in contact with it. How is the potential of polarizable electrode affected by solution composition? Non-polarizable interface can be polarized by passing of. We've already explained what is expected to the composition of the solution if a large current is passed through a non-polarizable electrode. See that electrochemical cell in equilibrium. A cell in equilibrium can be written as this. That's a cell loses electrons and becomes positively charged. This reaction can be split into a anodic half reaction and the cathartic half reaction. Remember, when you add the anodic and cathodic half reaction together, you find out that it will give you overall reaction. So we split this to get both of them. Remember, oxidation occurs at the cathode. That means the process electron is lost. You can see M loses electron. And then reduction occurs at the anode, just electron is gained. So you can see at equilibrium, redox reaction. The current flow can be divided into what? Cathodic current, anodic current. At equilibrium, the anodic current is equal to the cathodic current, and the current at that point is called exchange current density. And the one interesting thing about exchange current density is that it depends on the surface of the electrode. If you look at hydrogen gaining electron to become hydrogen molecule, experimental value for the exchange current density is found to be 10 raised to the power minus 12 and 10 raised to the power minus 3 amperes per centimeter square on mercury and platinum electrode. That means the electrode can affect the exchange current density. It depends on the surface of the electrode. So maybe you can see equation. Use the reaction. Write equation. Use suitable equation. Use suitable redox equation. For the reduction of hydrate. To explain the dependence exchange current density of electrode surface. You can use that. You can see the data already. on two named electrode cells. Electrode surfaces. You can handle that. Given a meter M, write equation to show the process taking place in the anode and the cathode and articulate. How is the current flowing in each case related to each other, and what is the major factors that affect such current? You can look at, I've already asked that question there. So I've already asked the question there. So you see the at equilibrium, the cathodic current is equal to anodic current, and the current is called exchange current density. So polarization at single electrode. At the anode, the electron is lost. At the cathode, the electron is gained. Any electron that is lost is gained here. So we can have the, so we can have cathodic polarization. And how do we now get cathodic polarization? By pumping in electron into the system. Why anodic polarization is by removing electron to the system. So I put it clear here that if we disturb the equilibrium by pumping electron to the system, that is increasing the number of electrons, since the flow of electron controls the flow of current. The equilibrium will proceed faster in the cathodic region directly. The potential will become more negative, and the cathodic current will now become greater than the anodic current. That means there is no longer exchange current density where the cathodic and anodic current is the same. If you pump in electron, therefore a plot of potential against current will slope downward, as you see, because it's becoming more negative. The electrode is becoming more negative, so it slopes down. And you find out in the other hand, if you now remove current from the system, that means you favor anodic reaction, and the anodic current will be greater than the cathodic current. The graph will slope or will rise upward, while the other one rise downward, just like you see in the next slide. So this is for anodic reaction. E is in each case is equilibrium potential. The equilibrium potential. If you trace that graph to this point and drop backward, that gives you the IO, that's the exchange current density. You can get that from that graph from that point. If you slope it down, get it from that point. Polarization and overpotential. E denotes the electrode potential, while E stands for the equilibrium potential. The change in electrode potential from the equilibrium potential is called polarization. Now, if this is the equilibrium potential, the change in electrode potential, that means it rises up. That is called polarization. Because it's rise up, it's called anodic polarization. If it changes downward, it's called cathodic polarization. So that is polarization. The difference between E and small e is called overvoltage. That's it. The difference between the new electrode potential and the equilibrium electric potential is called overvoltage. And overvoltage is written as this. It has been written there. The cathodic polarization, E. In cathodic polarization, you find out that it was sloping downward, so the E will be less than the equilibrium position. That means the cathodic overvoltage is negative. But in anodic polarization, you see E was going up, so that means capital E is less than small e, and Na, anodic overvoltage, is therefore positive. Consider a single electrode system. What do you expect if 1, current is pumped into the system, 2, current is withdrawn from the system? Provide a sketch of a plot of E against voltage for both systems defined in one above. In your plot, indicate and define equilibrium potential and exchange current density. You can see that when you see the point in the graph, when you trace from E, small e, the equilibrium current density down to where the graph starts and drop it downward, you'll be able to have the exchange current density. Also explain why the potential remains constant until the exchange current density is exceeded. And the answer is at equilibrium, IA and IA are equal. Initial disturbance of the equilibrium will not lead to a change in potential until the barrier is broken. What is polarization and overpotential? What is polarization and overpotential? Polarization we have defined as a change in electrode potential from the equilibrium potential. And we say overvoltage is the difference between the new electrode potential minus the equilibrium potential. And we expect that for a cathodic polarization, the new potential will be less than the equilibrium potential. That means the overvoltage will be negative. But for anodic polarization, since it rises up, that means the new electrode potential achieved will be higher than the equilibrium potential, and we expect that then that it is positive. Types of polarization, two types of polarization. We have the concentration polarization represented by that, activation polarization. Concentration is caused by charge transfer, concentration is caused by change in concentration of ions near the electrode or electrolyte interface, while the other one, activation polarization, is caused by charge transfer across the electrolyte interface. That's the difference there. Differentiate between the two types of polarization at interface and present an equation for expected total polarization. So you see that the total polarization, the sum of, will be the sum of the concentration and activation polarization. Over potential. Activation over potential, also called surface over potential, is the potential difference above the equilibrium potential required to overcome the activation energy of the cell. It is a potential difference above the equilibrium potential required to overcome the activation energy of the cell reaction to produce a specified current. It may arise through the accumulation of electron on the electrode surface, which can generate an energy barrier for the incoming electron. Provided mass transfer is not the rate limiting step, the relationship between the current and the activation of our potential is described by the Butler-Bowman equation. So we are looking at over potential, try to get some terms differentiated. Over potential, polarization, over voltage. Look at it that way. So activation over potential, that's the potential above the equilibrium potential that will overcome the activation energy of the cell. So that can be so. So now, Tafel found that for most electrode reaction, the overpotential is linearly related to the logarithm of the current as follows. So beta log I minus beta log IO. So that is what it looks like. But when you can now split it for anodic and the cathodic, and we have the anodic, it is given here. So this is minus logarithm minus makes division. So we have that. And for cathodic, we have that. We place the C, beta C, and we have that. Because of the minus sign, we divide and take beta C is common, log is common. So you take IC divided by I. Beta A and beta C are Tafel, anodic, and cathodic constant respectively. General beta is equal to 2.303 RT all over alpha NF, where alpha A range between 0, where alpha, that should be alpha, where alpha is, it range between 0, normally between 0 and 1. For most systems, it's always 0.5. Tafel equation. Let me take some questions here. Derive the basic Tafel equation and split the derived equation into anodic and cathodic, and split the derived equation to show the contribution anodic and cathodic polarization. Define the constant equation and calculate. The constant here is defined here. So for case you don't remember, this constant beta is given that. So you can see that the R is a constant, T is temperature, F is the Faraday's constant, N is the number of electrons, alpha is a parameter that depends on here. So I will give you value for R and expect you to calculate beta. when alpha equal to 0.7. Calculate the constant for the anode. When alpha, let's take this as, when alpha is equal to 0.7, temperature is equal to 300 Kelvin. The gas constant, you know, is 8.314. Well, the gas constant is stated there. Number of electrons N equal to 2. And finally, F, the Faraday's constant, you know, is equal to 96500. Hold on, approximately. How can you calculate this? How can you calculate? So we can, for the purpose of this work, we will take this to be anodic because this is anodic. You will calculate. And the next one is calculate the same value for the cathodic. So this will be equal to 2.303 times 8.314 joule per Kelvin times the temperature 300 Kelvin all over alpha is 0.7 times 2 times 9,654. Hold on. Alpha will not have any unit. So that is it. So beta alpha generally, beta alpha plus the beta value for the cathode plus the beta value for anode is equal to 1. That will be equal to 1 from here. From here, you can subtract your result you have for BA to get BC. That means BC equal to 1 minus BA. That's the solution. The future of Tafel equation. Tafel equation. The Tafel equation is an intensive parameter and does not depend on the electrode surface area. IO is an extensive parameter and is influenced by the electrode surface area and the kinetics or speed of the reaction. Note that the Tafel equation is restricted to the number of electrons N involved in the charge transfer control reaction, so the so-called symmetry factor alpha. So that alpha is symmetry factor. N is often equal to 1. And although the symmetry factor can vary between 0 and 1, it is normally close to 0.5. This means that the Tafel slope should be close to 120 millivolts if N is equal to 1 and 60 millivolts if N is equal to 2. So you can you should be able to outline the future of Tafel equation. and state the expected value from parameters that specify conditions. You can see the parameters here. I've stated them here. Alpha, and perhaps the toughest slope. Under what condition would the toughest slope be 120, and under what condition would n be 4 to 1, and the toughest parameter will be 60 millimeters if n is equal to 2. Question: calculate the expected value of the toughest slope if n is equal to 1 and 2 and 3. You can see the equation there. That has already been done. Write the general form of Tafel equation and split it to cathodic and anodic component. Identify all the terms in the equation. What does the slope of the Tafel cross indicate? And state the factors that affect the slope and also the exchange current density. Total polarization, Butler-Bowman equation. So you can see that from the Tafel equation, this is the activation energy for the anode and for the cathode. And if you add them together, that's activation of our potential for the anode and the cathode. If you add them together, we add this as we derived before. Then if we introduce the beta value, which we have defined before in theory, we can talk about it for both the anodic and the cathodic. And we have beta here multiplied by that for anodic and for the cathodic. If you follow on expressing that, you have for the anodic equal to this. So you can split this into two. One will be represent the anodic, the other one will represent the cathodic. And that gives you the log of IA over O is equal to this. IA over I is equal to exponential because of the logarithm function. Therefore, IA is equal to IO exponential of that. So what does that mean? That means we can relate it to the equation of a straight line. We shall see that later. NA will now be equal to this. And log IA over IO is equal to this. That is what you see there. What write the general form of Tafel equation, and from the equation derive the Butler-Bowman equation. Hence, define the following terms. The following terms and their significance. Exchange current density, to define that. Tafel coefficient. What is the relationship between the Tafel, the transfer coefficient of the cathode and the anodic? How can you use the transfer coefficient to predict the nature of redox reaction in an electrochemical cell? Watch out for the next slide. Log IA. So we can now look at it in the order, just like we did for the anodic, we can also do for the cathodic here, and therefore the same way. So this gives you, therefore IA is equal to IO, this as we derived before, and we can say that IA is equal to IA plus IC. We have derived IA and we've derived IC, we take them and add them together. But since it's negative charge, one of them is negative, it will come here. So we can now see that IO, you know the difference with IO down is just exponential addition. We now add the exponential function representing each of them together. IO is common there, IO is common there. You take IO and put them in bracketed terms. So this is the Butler-Bowman equation. And we now say I is equal to IO exponential this and this. That is the Butler-Bowman equation. So now if the transfer coefficient of the anode is equal to IA, alpha A, that of the cathode can be written as 1 minus alpha A, just like we did the other one, because the sum of the transfer coefficient is always equal to 1. We have done a calculation based on that. So that answers this question. But to have Bowman equation, you can see the equation is written. IO is the exchange current density when IA is equal to IC. IO is an index for intrinsic rate of electron transfer of an electrode reaction. The higher the exchange current, the faster the electrode reaction. Take note of that. Alpha is the transfer coefficient. It determines the geometry of the energy barrier, and it is an index that predicts if the electrode reaction favors anodic or cathodic reaction and apply both potential. IO exponential, this represents the rate of anodic reaction. This one represents the rate of the cathodic reaction. Butler-Bowman equation, the implications of the equation are the extreme condition of over potential being higher, highly negatively higher than above 50 millivolt. That means cathodic. When the over potential is very high, negatively higher, we say it's cathodic. When it's positively higher, we say anodic. increases while the cathodic current density becomes negligible. So when it is very negatively high, the anodic contribution will be 0. And we will have this. So the reaction will basically be cathodic, and we have this. And if you take I over IO, you have that. So you can now say log I over IO is equal to exponential of this. You can say like log I over IO can be represented as log I minus log IO. So if you take it to the right side, it becomes that minus this. Similarly, at positive over potential higher than 52 millivolt, anodic current density is much higher than cathodic, and you have this the similar equation. So if you now look at that equation, you can say a plot of this. If you take a plot, you take a plot of I, log I. If you take a plot of over potential, maybe over potential against I, now let's explain it for us. This is the cathodic expression. We have also derived for the anodic. So we can say that the over potential is equal to 2.303 RT NF 1 minus alpha log 0 plus 2.303 RT NF all over 1 minus alpha log I. So you can see this, we are subjecting this equation upside down. We are trying to make over potential the subject of the formula. And that is why we have this. If we make that the subject of the formula, we find out we are getting this equation. So if you compare this, you can see that this is the over potential. This is all constant, and we represent that constant here. And this is B log I. So we call this constant B 2.3 RT all over NF 1 minus alpha. We call that constant B. And you compare this equation with the equation of like find out if you plot a graph of over potential against log I, you have a straight line, and the slope will be while the intercept will be A. So this is what we call Tafel plot. Self-assessment question. What is over potential? Write Tafel equation for anodic and cathodic over potential. What is polarization, and what are the two major types of polarization? Show that anodic over potential can be written as this. That is what we do. How can this equation be useful? Explain the graphical implication. That's the answer, just like we did there. So we come to potential dynamic plot. This will represent the cathode and this represent the anode. If you take the slope of this line, it will give you the cathodic, that will give you anodic constant, and this one will give you cathodic constant. The cathode will slope downward, more negative, the anode more positive. And if you come to the equilibrium position and press it down here, the current here is the exchange current density. So we say that the higher the exchange current density, the higher the electrode reaction. So you see for the anode, there's loss of electron. For the cathode, there's gain of electron. That's what that graph. And this type of graph is called potential dynamic plot. A plot of E against log I. It's the same thing here. Anodic branch, cathodic branch, over potential, and the rest of it. What is potential dynamic plot? Of course, I've explained is a plot of potential against log of current that shows cathodic and this. What are the points that can be obtained from the plot? And exchange current density by extrapolation from the equilibrium potential. When you trace from the equilibrium potential in the y-axis and get to the point in the graph downward, you have that. Tafel slope for anodic and cathodic. Tafel constant for anodic and cathodic. Tafel constant for anodic and cathodic polarization. Obtained from the respective slopes. E, equilibrium electrode potential, redox potential of the cell. You can obtain that information from the sketch. The potential dynamic polarization plot showing both cathodic and anodic polarization. Indicate all the features in the plot is what we've said there. Work example, what is the significance of exchange current density and transfer coefficient in Butler-Bowman equation? What is the significance there? You need to know that. You can test yourself IO, you can test yourself alpha when alpha is equal to, when alpha is equal to 0.25, we say oxidation prevails. When it's equal to 0.5, there's symmetry, neither anodic or cathodic. That's a mixed type reaction. When alpha is equal to 0.75, reduction is favored. That's cathodic reaction is most favorable. And the conclusion, we can conclude that the change in electrode potential from equilibrium potential is called overpotential, and it is negative for cathode reaction, but positive for anodic reaction. Tafel equation gives the relationship between overpotential and exchange current density. And we see activation overpotential, also called surface overpotential, is the potential difference above the equilibrium potential required to overcome the activation energy of the cell reaction to produce a specified current. When a mass transport is not the rate limiting step, the relationship between the rate of redox reaction and current is given by Butler-Volmer equation. Butler-Volmer equation can be derived from Tafel equation. Information that can be derived from the slope of Tafel equations are one, transfer coefficient, direction of the reaction. We can say that in the next class, we should continue this concept. We shall continue to treat some questions before we go on to the next topic. So thank you very much as usual. We're happy to see you more, and we'll see you more very soon. Maybe next.